Hi everybody, my name is Jorge, and this is our work on lifelong inverse reinforcement learning. In a typical imitation learning setting, the user provides demonstrations of the desired behavior to the agent, who processes these demonstrations and immediately learns to replicate the user's behavior. If the user wants to teach the agent multiple tasks, then he would demonstrate each new behavior and the agent would learn it from scratch. This paradigm, however, does not allow the agent to reuse knowledge that is relevant to different tasks, which causes the need for the user to provide numerous demonstrations for each desired behavior. As a solution to this problem, some authors have proposed for the agent to process all demonstrations together. This allows the agent to exploit information common to all tasks, thereby reducing the number of demonstrations required from the user. This unfortunately comes at the cost of the agent needing to wait for the expert to demonstrate all behaviors before starting the learning process, which is not viable in a lifelong learning setting. Our solution has the benefits of both of these approaches. The user will provide a small number of demonstrations for each new task, and the agent will immediately do its best to replicate the demonstrated behavior. Upon receiving demonstrations for a new task, the agent will combine them with any relevant information from previously demonstrated tasks and rapidly replicate the new behavior. Inverse reinforcement learning is a framework for imitation learning in which an agent is trying to learn to act on the world via reinforcement learning, by executing actions and observing resulting states and rewards. However, in this setting, the agent does not have access to the reward function and is instead allowed to observe an expert user. The user acts on the world for some time, and the agent then infers the reward the expert was trying to maximize, and finally uses it for typical reinforcement learning. Formally, in maximum entropy inverse RL, the agent is given access to a set of expert trajectories, each of which is a sequence of state-action pairs. We assume a linear parameterization of the reward function, and we further assume that the user acts according to a maximum entropy distribution that exponentially weights trajectories according to their reward. The goal of the agent is then to maximize the likelihood of all observed trajectories. In our lifelong learning problem, the agent will be faced with a sequence of tasks, each of which is an MDP without a known reward function, and the goal of the agent will be to learn the set of all reward functions. For this, upon observing the nth task, the agent will strive to maximize the joint likelihood of all observed trajectories across all tasks, with a reward prior chosen to encourage tasks to share structure. Our algorithm for solving the problem assumes a factored representation of the reward parameters and uses a sparsity prior. Intuitively, we can think of each column of the matrix L as a chunk of knowledge that can be reused across tasks, and the S coefficients as sparse, task-specific coefficients that select which chunks of knowledge are relevant to the current task. This allows us to convert the optimization problem to a sparse coding and dictionary learning problem, which we can solve efficiently online. We were able to obtain improved performance over the single task-based learner maxent with little computational overhead. By introducing a simple re-optimization of the reward models, our method was able to surpass IRL via Gaussian processes at a substantial speedup.